Hello everyone, welcome to the meeting. This is the presentation of cross-model conjunctive query over relation and tree structure data at DASFAA 2022. The topic today will cover the motivation, contribution, and the application of this topic. So first of all, the motivation. One of the big data challenges here, the variety. The data can be in different forms. For example, some logs in Internet of Things are JSON and XML. When we do analytics to this data, we need to combine them together. We need to connect them by some common information. So for some joining cases, the final result can be small, yet the intermediate result during joining can be really huge. So the worst case join algorithm is the key here to guarantee certain amount of intermediate result size in such cases. The topic is very much of theoretical interest in relational algebra, yet we think they have really big potential in new applications like data lake, polystore systems, or the multimodal databases. So now let's move to the worst case model that used to find the size bomb. So the size bomb for a join query is the cardinality of the join result in the worst case. The model is called AGN model. So AGN is short for three authors named. In this model, a table size is the full combination of attributes unique values. The common sense of the size bomb for two table join is n squared. Now let's see how we find this number by this model. So in this case, we want to find the size bomb of the result of ABC. So if no constraint, the size bomb could be n to the power of 3 by the Cartesian product of each attribute. But we have some bounded tables, as we assume each table is only with n rows. So the Cartesian product of AB and AC tables are both constrained to ON. So by these linear programming constraints, we can achieve the maximum solution, which is the n squared, by giving A and C to n and B to 1. So what does this n and 1 mean here? It is exactly the unique values of the attributes. This means that by giving n unique A and C values and only one unique B value, we can achieve n squared final result, which is the size bomb. So for simplicity, we do logarithm both sides for the linear programming. So the product becomes additions for the subjectives and the constraints. Now 1 and 0 means n1 unique values and n0 unique values. So by AGN model of the linear programming, we can actually find the size bomb. And by solving the size bomb, we can know how to construct the instance by the number of unique values. So now even given a really complex query like this one, we are able to find the size bomb of it just by maximizing the Cartesian product of all unique values, constraining each table to ON. So the size bomb for this query is n to the power of 4. So next, we're going to talk about our contributions. So we add tree pattern query to this research problem. So first of all, what is a tree pattern query? The traditional tree data are XML and JSON. The tree pattern query we discussed in this lecture is PC parse and AD parse. So a PC parse is to find the value matching between two attributes having parents and children relationship, while an AD parse is to find the value matching where two attributes having ancestor and descendant relationship. For example, in the first simple JSON document, when querying by AB PC path, we will get the result of B1 as we find A, which is parents of B. When querying by AD path, it will also get the result of B1 as appearance is also an ancestor. So for the second simple JSON document, when queried by PC path, it returns nothing because no parent-children relations between A and B. When querying by AD path, it returns B1 value as A is the parent of C and C is the parent of B. So A is the ancestor of C, which is matching. So just like assuming table size to be ON, we assume tree instance size to be ON or the nodes of each attribute to be ON. We may easily find the size bound for PC path and AD path. As for PC path, each child has only one parent, so it is connected one by one. So the maximum connection is the children node size. Also can be the parents node size, which is ON. However, for AD path, it may have full Cartesian product connection between the ancestor and the descendant nodes. So PC is very similar to a relation constraint that a table is bound to the ON, while for AD path, it is like with no constraint to two tables. So things are going more complex when we combine branches and AD paths. So from the left figure that we bound each PC path to a constraint and each AD loops to no constraint, we get the constraints of three equations. By this constraint, we get a solution of 3, meaning the size bound could be O n to the power of 3. But this is not correct. We cannot achieve this size bound. The size bound is actually n squared. The reason here is that when we have branches and AD paths, they have conflicts when both generating n squared results. So the size bound becomes an alternative. That means the worst case instance can be constructed in different ways. So the first contribution is that we can find the size bound for tree patterns. PC is very much similar to a relational table, which is constrained to ON, and AD is no constraint to anything. However, when combining branches and AD paths, we can find the size bound from the alternative construction of the constraint. And actually, the maximum value of all alternatives is the size bound. So the size bound is not directly affect the worst case optimal join algorithm, but it is the indicator, also the proof basis for the worst case optimal join. So a worst case optimal join algorithm guarantees that all generated intermediate results are less than the worst case result asymptotically. We here introduce the relational one and make some changes to fit the cross-model context. So the traditional way of joining is usually pair join. For example, for triangle join here, when you have 3 tables, it will like join 2 tables first and then join the 3rd one. So in this way, you cannot guarantee worst case optima, as any two tables join may generate ON square result. But we show that the final result is less than ON square result. So the correct way to do it is to join one attribute at a time by computing all related tables at the same time. And there is actually a very important property to support this is that the projection result is always no more than the final result with the same constraint. So apparently the projection cannot make the result larger. So how are we going to do this example? So we first is to compute one attribute results, and then we compute the result of 2 attributes, and then all 3 attributes results. For example, we can compute the result of A first, And then by this result and the original tables, we find the result of AB, and then finally the result of ABC. Since we all only generate the result of the projection or the final result or the intermediate result, and final result will not exceed the size bound. So this result is only the projection, so the result is less than the final result. So the intermediate result of A, AB, or ABC combination are all less than the final worst case results. So adding tree pattern to make things complicated, it is required actually to decode and encode the tree position to intermediate form, because we want to join the relation and tree data at the same time. However, this position value is out of our interest to the final result. And some pattern, as we discussed before, like branches and AD patterns, are very easy to scale to massive intermediate results. So we designed to compute the past result first and remove the irrelevant position value. And then we can join the tree pattern and relation result together and simultaneously, and to reduce the intermediate results. So our design of algorithm can guarantee the worst case optima for most cases. Yet for some other cases, it may require the information of some position value that is more than the final results. So now we go through our algorithm, which is called the CM join, which first transform tree data into intermediate node tables with both position values and the label values. Then we compute the past result first and project out non-branch position values, because we only need the branch node position value to matching between paths. And the label value can be joined between tables and tree data. Then we can apply a general worst case optimal join algorithm only to process two different forms of data simultaneously. So when we compare the algorithm with some different cross-model solutions by diverse data set and complex queries, in general, we generate less intermediate result and have a faster response time in most of the cases. The reason is that these compared solutions usually generate massive intermediate result during the joining, just like pairwise join in relations. So last, the application in this field. So to be honest, this topic is now mostly theoretically interesting. The advantage of the method is just like the nested loop can be speeded up by building index like hash table, then join. So in databases, no matter single model or cross model, if complex queries can be detected, this worst case optimal join algorithm can be applied. And for sure, we cannot guarantee the best performance by this algorithm, but we can guarantee that in worst case, it's quantified worse. It cannot be worse than the worst case situation. That is worse is predictable. For the current commercial database, as far as we know, MarkLogic is using this technique in their engines. So this is the end of the presentation. Thank you for your time.